Okay, so let us cover the remaining topics of optical instrument in this class. Right. So let's start with compound microscope. Compound microscope. What happens in compound microscope means uh, we use a small objective. Two lenses are there. There is a objective lens and there is a eyepiece lens like this. This is the optical axis. There is an object kept here. This is the objective and this is eyepiece. So what happens? The rays are coming from here and this is the ray which is going to hit here. Then another ray also you take. Another ray you can take passing through the center and hitting somewhere here. So we can see that this is the image form. So this is height of object and this is height of image. But this again these rays which are coming here, this has to go, of course they go like this way, and this ray which is coming here, it also passes, but these two rays are diverging rays, so they do not meet, right? So we need to extend them backward. When you extend them backward, and this also when you extend them backward, they appear to meet somewhere, and this is the final image that is called as HI dash. That's the final image which is formed. So this is how this is working. So here of course note that this point is the objective focus of objective and this is the focal length FO. Now this image is formed here at this place. This image is formed within the focus of eyepiece. This is important thing to note that. So this is the image distance of V objective. This is U objective. Okay. This is focal length. For eyepiece, this is the objective object distance for eyepiece. This is the image distance of eyepiece. Okay, image distance. Focus. This is the focus. So this image which is formed by the objective act as an object for eyepiece, and this should lie within the focus so that we can get the virtual image of that, right? So now here also two cases are there, two important cases are there, like what is the case when we are getting image we want at least distance, or we want image at infinity. Okay, let's take these two cases. So first case is, and how do we calculate the magnifying power here? The magnifying power is calculated as uh, magnifying power of object multiply eyepiece. Okay, this is how we calculate total magnification or net magnification or magnifying power. So we calculate objective and eyepiece. So eyepiece, now let us say that we take first case where final image is formed at infinity. Final image at infinity. Final image of infinity means eye is relaxed. Eye is relaxed. So this is the case which is final image is infinity, eye is left. That means this is forming at the focus of this. Okay. So that means this object distance for eyepiece is the focal length. We are talking about distance, not writing this sign. I am talking about distance, so I will write it is equal to the focal length. Or with sign I can put minus f. Okay. And image is forming at infinity for eyepiece. Image is forming as minus infinity. Okay. That's the case. So now we can directly say that This is the case where the magnification formula for eyepiece becomes equal to d by uh, fe. You remember? I think this formula, because this is acting like what? This is acting like a simple microscope, simple microscope or magnifying glass. So that's why magnifying power will take d by fe because image is format infinity. Okay. But suppose image is not format infinity. So in case number two, if you take when final image formed at d equal to 25 centimeters. In that case, the magnification of eyepiece is 1 plus d by f. Correct? If I remember correctly, this is the formula, right? Okay, so the only thing is that we need to know MO. How to know MO? So, magnification of objective can be written as V by U, with proper sign we will put, or we can use as F by F plus U with proper sign we will put, and this can also be written as F minus V by F objective. Okay, this is what it is. So here we can use any of this formula to calculate. Any of this formula we can use to calculate this, right? That's the formula. Now suppose, uh, any doubt in this? No doubt. Okay. Okay. So suppose now the thing is that I want to use this formula. Let us say I want first case. So in first case I want magnifying power. I am writing as net magnification. Okay. So I want to calculate net magnification for first case. So this F0 minus V naught by F0. So where this image is V0, we need to calculate, and also note one important thing, very important thing, that the distance between this focus and this focus, that distance is called L. According to NCRT, let us follow NCRT. According to NCRT, this distance is called L. L. Okay. So, and this distance is already focal length. So, V naught is F naught plus L. That is an important point to note that. V naught is equal to, note that V naught is equal to F naught plus L, where L is the distance between the objective focus and eyepiece focus. That means the second focus of objective and first focus of eyepiece. Okay. This we know. So, suppose if I use this formula, so I will substitute V naught here. So F naught minus V naught is F naught plus L by F naught. So sorry, I am calculating objective first. First I am calculating MO. So from here this get cancelled and you get minus L by F naught. Right? That's what we get. Now let us calculate net magnification. So if I use net magnification calculation for the first case, this is MO. MO we will use as minus L by FO into ME, which is D by FE. So this formula is such a simple formula, we can use it, right? This is the first case. And second case also, let us use the second case. In second case, this will remain same. Net magnification, this will remain same, minus L by FO. But that one will become 1 plus D by F. That's what the formula will be, right? So these are the two cases where we can quickly solve problems on this. Okay. So that's what it is. Compound microscope is over. Then we will go into telescope. 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 Telescope, here we are talking about astronomical only. Astronomical telescope. And in this telescope, we are talking of first refracting telescope. Refracting because we are using lenses. Lenses are used. So in this case, this is a big like this, and this is a small. And also note that in case of compound microscope, if you see the formula FOFE, generally here note that we keep FO smaller than FE. This is the case, means this happens in this case. Why do we keep it like that? Because one important reason is that the objective has a smaller focal length and eyepiece has larger focal length, so that wherever the image is formed, that image formed within the focus of eyepiece. Eyepiece has large focal length. Eyepiece has large focal length. So wherever the image it will form, in between only it will form, and that image will lie within its focus. That's the reason. Okay. And also note that if you keep FO small, it will be large. Magnification will be large. So that is also important thing. We keep it like that. Okay. And in this case, telescope. Let us try to understand telescope like this. So rays are always going to come parallel here in case of telescope, and these parallel rays will converge at the focal plane. Focal plane means somewhere at the focus. I think this diagram I have to draw a little bit proper, otherwise it will not happen like this. Somewhere here it is forming. And the rays, it's not that rays stop, rays goes here and will be coming here. And then these rays will be diverging again like this. Diverging rays will be collected by the eyes. So eye is there that side. Eye means here eye will be there. So eye of the observer will get that. Now this way you have to extend this back side, and this is the final image. Anywhere it can form, but I take, let us say it is forming here. This is the final image. Okay. So here note that this angle, um, these rays are coming very parallel to this, so they are meeting here. Let's take that this distance, and they are going to meet at the focus. So this distance here is the focal plane. So this, of course, here if I show the image, this is the image, and this is the final image. So this distance from here to here, this distance is focus of objective. This point is F0, and note that this point is also the point FE. So the same point is objective focus and eyepiece focus. Okay. Then you may say that how the image is formed. So note that this is very close. So these rays are also coming from this. These rays are also coming from directly, because from this object so many rays will be coming directly also. Okay. I have taken only one ray, not solid line, it's a dotted line only, because all these rays will be going in there and all these dotted line will come. So note that when you extend them, this and this are same thing. Here what you need to note is this angle alpha, which is going to be same as this angle alpha, and this angle is beta. So what is angle alpha? Alpha is the angle, um, I think, did I draw the diagram correctly? Because ray of light I am taking like this way. But in NCRT they have given coming like exactly like this way they have done. Anyway, it doesn't matter. I can take it like this way also, because rays have to be parallel. But they have taken passing through this point. So okay, this diagram is also correct. Um, no, no, not parallel to principal axis. They have taken inclined. Passing through optical center, they have taken. They have taken passing through optical center. They are parallel only. Here also they are parallel only. But the thing is that they are passing through this optical center. That is what, but still this diagram is not wrong. Okay? This is also correct. So if you take like this angles, then note that let us say that this is some let us take y. Okay, so what is alpha here? Alpha is equal to y by fo, and from here also alpha can be, this is height of image, note that this is height of image. So this distance will be how much? This distance we do not know. Okay, leave it. Beta I think we can calculate from here. Beta will be, this will be Fe, this will be definitely Fe, and this is Hi. Okay, so beta can be calculated as Hi by Hi by Fe. Hi by Fe. Alpha beta. Right, that's what it is. But what is y here? I think that is what in NCRT they have done. We need to change the diagram. NCRT they have not considered y itself. That's what it is. Okay. Diagram you make, then it will be different. Then from here we will not be able to calculate. That's why NCRT diagram you follow. NCRT diagram is important to follow. Okay. So draw this. Then take optical like this, and take the rays coming like this way. One of the ray you can take passing through this like this way, and another ray you can take it like this way parallel. But this ray has to convert, because this ray will not convert because it is passing through optical center. This does not converge. This has to converge, and it will convert somewhere here. Okay, like this. So this I think I need to make little bit bigger. So this ray is hitting here, this ray is hitting here. Then they are going like this, diverging, and then they have extended it, right? And this is the final image. Okay. So here, what is important is this image Hi, and this is Hi test. Okay. And this angle they are considering as angle alpha. Incident rays are making angle alpha with the optical axis at the objective. Okay, and this ray, final rays, are making angle beta here at the eyepiece, alpha beta. Okay, and note that this is very close, so they are also making the same angle beta here at this eyepiece. This also is angle beta. This is how they are doing calculations. So this distance is FO, and this distance is FE. This point is also the focus of objective, and this is also focus of eyepiece. Okay, same point it is. Now, if I take this angle as alpha, this angle as alpha, right? So this angle also become alpha only. So now take alpha here. Alpha is very small. So tan alpha is hi by fo. And if I take tan beta from here, or beta, that become hi by fe. Correct? Hi by fe. So now if I take Final image is forming, if I take final image form at infinity, that's what is the case. This is the case, right? Final image is forming at infinity because this image formed by objective is at the focus of eyepiece. So this image which I have shown this image, right? Actually, this image should be taken at infinity. So these are parallel. This is not meeting this side actually. These rays are not going to meet here because this image is at the focus. So this ray is actually becoming parallel. So it is not going to meet here this side. It will be meeting here at infinity only. I have shown here, but this actually is meeting at infinity only. Correct? This diagram is very important to correctly draw because we are drawing without any skill, na? Without any skill means where the straight lines are going, you have to properly draw. It is going parallel. It is forming at infinity. So this image is forming at infinity. This is going to be at infinity. Okay, minus infinity you can say. This is the eyepiece. Image distance for eyepiece. Okay. So for this case, now let us calculate the magnifying power. Magnifying power. Magnifying power. So magnifying power is beta by alpha. Note that beta by alpha. So beta we have got hi by fe and it has come hi by fo. So that's the result fo by fe. This formula for total magnification or magnifying power, right? Net magnification. That's the formula fo by fe. Net magnification or magnifying power. When final image is formed at infinity. Case 1, final image at infinity. Right? Final image at infinity. That's the case. It is the case of relaxed eye. Clear? Right? This formula FO by FE, remember that. Now, case 2, very important case, case 2. What happened in case 2 is that, note that these rays which are coming here, they will be coming in the same manner, okay? These rays, first ray which is coming like this, it will come like this, passing through optical center. And second ray is meeting at this focal plane. So this point here, where the image is formed, this point is the focus of objective, but this is not the focus of eyepiece now. Eyepiece focus is coming here, okay? So that means this length from here to here, this length uh, is the length of objective and this length is eyepiece focus. Now because this image is lying inside the focus, now what will happen is these two rays you take and then you show it diverging, right? So when it will be meeting here somewhere, rough diagram again. So this image that we are going to take, this image, right? So this image is hi and this image is hi dash, hi dash. Okay. Now here, how do we calculate the magnifying power? Magnifying power, how do we calculate? Magnifying power. And we want that image has to form at least distance. So for eyepiece, this is minus t. Okay, this is minus t. How do we calculate now for this case? Alpha you will calculate in the same manner alpha. Right, this is the same angle alpha you will calculate. Alpha will remain, definition of alpha remains same, hi by fo. But how will you calculate beta now? Beta. Beta calculation is how? How do you calculate theta? Theta means this angle, this angle, or let us say you define here these angles. So you may define here also beta. But this distance we do not know, no? We do not know this UO. UO is smaller than, sorry, UE. UE is smaller than FE, right? We do not know. But this beta we can define as HI by U, HI by UE, correct? We define. Okay, now very interesting thing to note that we know 1 by V minus 1 by U is 1 by F. Let us apply this for this eyepiece. Let us apply this. Let me consider them as this apply formula. So here VE becomes minus D here, minus 1 by UE is 1 by focal length of eyepiece. So 1 by UE becomes equal to minus 1 by D plus 1 by FE. Very important, very important. That's what it is coming from. Now when you take magnifying power or total magnification, net magnification or magnifying power, we take beta by alpha. This is the definition. So here when you take HI by UE and you take HI by FO, you get FO by UE. Now 1 by UE we will substitute from this. 1 by UE we will substitute from that. So 1 by UE is what? Minus 1 by D plus 1 by F. Very important formula. Here only people get confused. So this magnification is minus FO. If you want, you can take inside. So FO by D plus FO by F. That's the magnification formula when the final image is formed at least distance. Are you clear about this formula? Very important. That's the second case. I think I have not written the case. Let me write this case. This case is when final image is formed at least distance. Final image formed. Final image formed at d equal to 25 centimeters. That is the case 2. Better we remember this formula. By the way, if you forget, you have to think of this approach only. In your board exam, definitely 5 marks question chances are there. They will be. Okay. So we need to clearly define and see here FO, FE, FO, these D, all these are in magnitude. So minus sign which is coming, that is showing the image is inverted. Final image is inverted. Note here that final image is inverted with respect to object. Okay. And final image is virtual image. This is where people don't understand. Virtual image is inverted here. Okay. Final image is a virtual image. Virtual image is inverted because it is with respect to the object. With respect to the, because this is second image, this is first image. With respect to first image, this is erect only because first image is also downward, second image is also downward. So relative to first image, second image is like erect only, you can see, because both are inverted only, right? But with respect to object, it is actually inverted because object is erect and image is inverted, right? Clear? So that's what it is, telescope. So with telescope, we have finished everything. Cassegrain telescope is there. Reflecting telescope is an important thing. That quickly let me discuss that. That is not much there in detail. See here, if you see the formula for magnification now, this magnification previously the magnification which we derived, it comes as FO by FE in this case, right? This FO by FE comes. Now, if you want to increase magnification, FE should be small and FO should be large. Okay, but the thing is that you cannot increase very large because there is a problem in manufacturing, cost problem, handling problem, transportation problem. Many problems are there, so we cannot do that. there are some limitations of this because of this problem. Okay, this telescope has limitations. Another limitation is that these lenses are not manufactured properly, so the lenses will behave like a prism. Okay, instead of making images, they will start showing dispersion effect. So that is called chromatic aberration. Chromatic aberration. So lenses have chromatic aberrations where the rays of light will have dispersion after passing through the lenses. So how do we correct it? We will have problem. That is why we are going for mirrors now. Mirrors are used for making telescope. That is called Cassegrain telescope. Okay. So Cassegrain telescope is a reflecting telescope. Cassegrain telescope is a reflecting telescope. Reflecting telescope. And how does this work? So we have like this kind of mirrors are there. A convex mirror is there, and concave mirrors are kept. And here also like this concave mirror is there. So rays of light which are coming like this way, these rays get reflected here. They get reflected here. I think I need to show this properly. So these rays are going to hit it. After hitting, they go like this, and here they will be meeting. The image will be formed, and here there are some kind of lenses are there, okay, which can be used by an observer. There will be observer sitting here in this space. Okay, we will be getting the image of that. Now here, note that this lens is called. This is a convex lens, and this is a concave. So this is a primary mirror. Primary mirror. Primary mirror is concave, and this is secondary. Secondary mirror. This is convex. Good. So that's how it will work. And in NCRT, there are one or two questions on this. One question definitely given in NCRT, very good question. You can expect if any questions are coming in your board exam as well as for NEET on Cassegrain telescope. Okay. So the idea here is that suppose if this is not there, now if this is not there, so the image which is formed due to this, it will meet here. This ray will be meeting here. This is the first image, but this first image acts like a virtual object, and then final image I2 will be forming here. Okay, so like that we can consider. So first image I1 can be taken as a virtual, and then I2 is a real image. That is made at the observer. But the problem here is that observer has to sit in this limited space, and because of the limited space, there is not so much rays coming. Okay, rays also get blocked in between because of the mirrors. So there are some problem with this also, but this is better than lenses, okay, because this is cheaper also, and defects can also happen in this. There are problems of spherical aberration. Spherical aberration means the surface is not perfectly spherical. So the mirrors which are manufactured, they have not perfectly spherical mirrors. For that case, we can correct that mirror by making use of parabolic mirrors. Parabolic mirrors can be used, and we can correct that error, right? So that's what it is. I think we are done with this chapter, right? So now you work out problems, solve all the type of questions. I will be creating some online test papers, okay? So few papers I will create today. Tomorrow you can write at your convenient time. Okay, fine. Then let us see in the next class. Okay? Okay, Sam. Okay then. Bye bye. Good night.